nanohub.org.
So I would say now you guys could go to the NanoHub, and we'll go to this tool called PCPBT. It's a really cool acronym, right? So each tool has a little tool page, right? I just typed it in on the top. You can type it in the search box and get there. There's multiple ways to get there. You can probably type PCPBT in the search box. Or you can type Klimek and piecewise, or everybody. There's actually now a topics page that explains the PCPBT tool. You can click on. That's interesting. Okay, so everybody sort of is there? Yes. So everybody launched the tool, please. Oh, you guys, some of you launched the video. That's fine too. Not sure if you're familiar with this. So here's a pretty big window. You can, on the bottom right, you have this thing that looks like on Windows, like a make big button. You could pop this window out. Okay, so you can have the whole thing on your screen and you can make it bigger like this. Okay. So this tool allows you to do like double barriers like this. You can do a variety of things. So if you go on the top left, it allows you to do like 1 barrier, 2 barriers, 3 barriers, or n barriers. Okay. So the 2 barrier device is depicted by default. You can pick a 5 barrier one, and then at will control the barrier heights, for example, here, okay? No, in this tool, you can choose the barrier heights and the effective masses. Well, the barrier height and the material, effective mass make a material, right? So this is a teaching tool, right? This is a tool for concepts. If you want to do a real RTD, we'll go to the RTD negative tool, and you will say, I want to do aluminum gallium arsenide at an aluminum percentage of 30%, and it'll pull out what the conduction band edge is and the effective mass, right? This is a teaching tool for understanding potential barriers, etc. Okay? And then, so you have 3 choices. You can change the geometry, so the length of these regions. You can change the effective mass and the potential energy. All right, so at some point I wrote down here. All right, so this is a very simple one, right? It asks for going to a double barrier device and hit simulate. And here you have a composite plot like this with the resonant barriers, with the barriers and the resonant structures. You have the transmission coefficient and you have the position of these energies, right? Pretty simple. So now we could go back to structure, and we can make these barriers shorter, for example. So what do you think should happen? Any wild guesses? The resonances should be wider. That's right. So it's running right now. So So here are the two results. You can put them on top of each other with all, right? So here's the second simulation, here's the first simulation, right? And you can compare them like this, right? So it's pretty clear, right? So taller barriers make resonances lifetimes longer, right? I think here's also, excuse me? Oh. Here's this comparison to bulk band structure. So here's this thing of that I had just in the lecture. If you have a tall barrier, here's the natural resonance, here's the second resonance, right? But if the analytical solution would have predicted for a particle in a box, the energy to be here. Okay, so actually the resonance has lowered that quite a bit. And in the lecture this morning, I used sort of this projection method of saying, okay, a ground state should be at pi over L, right? And I have a parabolic dispersion, and I start from here and I'll go to here. This is where this sort of comes from, that picture, okay? Does that make sense? All right, so I'm going to do something that's not on the script. Let's see if it works. So what would happen if I do this? I make the barrier 0. Like this. What would you expect to see? Transmission of 1 above the conduction band edge, and that's it, right? What if I go in and make this mass in the barriers bigger, like this? It's just a mass, right? What should happen? The eigenenergies would be decreased. What does that mean?
Energy levels in this n square pi square divided by pi n.
Okay, so, all right, so what that means is, let me try to translate it in how I think about it. You have a wave that's propagating, right? And in a certain region, it would propagate slower, right? Because the velocity is slower, the effective mass is heavier. And then here it propagates faster again, and here it propagates slower and then faster again. All right? So there's a modulation of your wave propagation. The thing should be roughly the same as a double barrier structure. Okay, so let's see. And so this plot is not as nice because there's no barriers here anymore, right? But basically, you have a transmission coefficient that indeed is not just 1. Okay? So you've built in a quasi-bound state just by modulating the effective mass. Okay? And it's not a small effect. It's like 20 millectron volt effect here, right? That's 1 kT. Okay? So the point is, if somebody shows you a quantum transport simulator that says, I don't vary my effective masses, all I vary is my barriers height, you should laugh him out the door. Because a different material has a different effective mass, and you can't neglect the effective mass variation. Okay? All right. Let's see. So we looked at the barrier heights. I didn't do the widths. We looked at the bulk band structure output. Do you guys, is that all pretty clean? You understand it? Okay. All right. So then, before we do the next exercise, let me show you another one I like to try. Let me clear this graph. And I'm going to put this effective mass back to 0.067. By the way, you just gave me a good idea for a tool improvement. I can have default values that suggest what gallium arsenide would be or indium arsenide would be in terms of masses. That's pretty easy to do. So I don't have to remember that the gallium arsenide effective mass is 0.067. All right. But what I like to play with a little bit is for example, a 5-barrier device. And here, the standard result is this, right? 5 barriers, 4 states. Transmission coefficient is 1, okay? So, have you guys heard of chirped superlattices? No? All right, so let me show you what a chirped superlattice is. What you do is you modulate the barrier height. For example, you set it to 0.2, 0.25, 0.3, 0.35. Okay, so you have a sort of a ever-increasing barrier. Any wagers how this thing should look?
Have some
Minutes.
increasing thing in band structure, like a frequency or a wavelength.
Mm-hmm. Should it be? What was that?
Small band gap.
Smaller band gap. And why do you say that?
So this structure is repeated.
Mm-hmm. Okay. So I think the band gap is wider. I haven't done this one, but I think it's wider. And I think it's wider because some of the barriers are lower, so the coupling is stronger, so the bandwidth should be wider. And so here you go. So here's the original in light, now in dark. Seems like it's, so I increased the width like that. And why would you do such a thing? Well, if you actually applied a voltage of that much voltage difference over the barrier height, they might being roughly of the same height, and you might end up with a more symmetric structure again. So some people want to build a superlattice, they want to build a mini band, but they want to make it a symmetric mini band. That means they need to chirp the barrier height in order to compensate for the voltage drop. Okay? So you can play with things of that nature. Good. So now I would say, if you're on here, close this. Let's go to another tool called RTD and NEGF. RTD and NEGF. Yes?
So these kind of structures are generally there even in case of solar cells, right? So, I mean, with a gradient of concentration in aluminum or
Right.
whatever. So, if there is some kind of this kind of tunneling happening, then will that kind of a structure be effective or bad for PV solar cell kind of?
I'm not quite sure. I understand people build chirped heterostructure like that, and now are you asking me what?
Like if we have like a continuous set of potential wells, like in this case, then the energies will just be tunneling through rather than us having an electron hole pair.
Ah, okay. So that's a balance. So these devices need to strike a balance between providing the right density of states to absorb photons, and then to also carry them away electrically, right? Carry the generated electrons and holes away. So that's a tricky balance, and that's part of the solar cell design. All right. So this tool is actually relatively similar to this NEMO tool I had talked about this morning. Completely different interface and completely different engine under the hood. But it allows you, if you just click simulate, it'll run for a little while, like a minute or so, and it'll ramp through the voltages and compute a current voltage characteristic. Ian, did you? Art? Oh, no, just kill the last two lines, the last two elements. Oh, sorry, that's fine.
What did you say?
Yeah, just kill this guy, yeah, that guy, and session.
Oh, all of that. Okay.
So now you can just launch it. All right, so now it's processing some graphics, right? And here's my favorite device, right? Resonant tunneling diode. There's a resonance, there's a peak, look aligned with that, right? And I can go in and ramp up the voltage. And on the right, what you see now is in blue, the transmission coefficient. In green, the current density as a function of energy. And in light green, the integrated current density as a function of energy, okay? So again, you can see how much current is really flowing in the ground state here. And you can see the current rise as I increase the voltage, right, on the right. So now we're at peak voltage right here. And even so, there's quite some current already flowing in the excited state that is up here. All right? And as you ramp the voltage further, you start to cut down on the on the current. And there's a little bit of current flowing still, and you can see it's basically aligning with this band edge here, okay? So by default, in this tool, we have turned on this relaxation in the reservoirs, okay? Because it's a good thing in general. So if we went in and go on the advanced and turn off the relaxation in the reservoirs and set it to 0, okay? Then, and hit simulate, then we'll get a slightly different result. Right? Then we will not have an occupation of this triangular well that is in the notch. Okay? And you had a question about something. Does it make a difference whether you include the all right, so we can pop up this other tool one more time. Well, let's stay on this one and then we'll try to answer that question. All right, so here is now the calculation without a relaxation in the reservoir. And here is it with. Sorry. So now, yeah, so the peak current changes, right? There's a little bit more valley current. We can go into here, hold on. Current voltage characteristics. So here are the two results. One with and one without the relaxation in the reservoirs, okay? There's one thing we haven't talked about in this morning's lecture, which is the charge density. We haven't looked at that in some detail. Let me pull this up here. So here is the central resonance, right? Here's the transmission coefficient, and here are the traces now of these eigenenergies, okay? So I'm ramping through here, and you can see how the resonance is coming down. Now it's about to hit the Fermi sea right here, right? The resonance is here, it's hitting the Fermi sea. it's now almost at the maximum of the current, and then it goes down, right? So what's plotted in this panel here is the semi-classical charge in the system. So here's the doping, here's the semi-classical charge in the device. That's not a quantum charge, right? It's square, it's a semi-classical charge, and you should ask yourself, does it make a difference if you calculated things quantum mechanically? The thing is, it takes a little longer to compute, so by default, we have it turned off. So let me go in, and I'm going to turn on this Hartree self-consistent calculation, okay? And I hit simulate. It's going to take a little longer to compute, but what it does now is, doesn't semi-classically, previously it calculated the charge semi-classically, and then did a one-pass non-equilibrium Green function calculation on top of that. Now, it calculates the NEGF, gets the charge and the current, distributes the charge across the device, recalculates the potential, calculates the NEGF, so it needs to converge a little longer. And you can see here it's taking early on 5 iterations, then 2, 3 iterations of repeated calculations of the charge and the electrostatic potential in the quantum transport formalism. Okay? So it takes a little longer to run. We're trying to actually get information to the users. I hope this is useful, where you sort of see an activity level here on the bottom, right? It's not frozen. We try to get feedback that this is not a hanging tool. Building that into tools seems like sometimes pulling teeth with students. They're like, well, it runs, right? But I think users really want to have some feedback. So we're almost done. This runs till 0.5 volts. Yes?
Time is from free electron state to the bound state.
Can you repeat the question?
The relaxation time
is
for free electron state relaxed to the bound state.
That's right. That's the broadening of the state in the emitter. Okay? And the broadening is applied to emitter and collector, just next to the barriers, not inside of the device. Okay, so now I can go in and look at the bands, the resonances, the charge. And here you can sort of see, indeed, now this is actually quantum mechanical charge, right? It's not piling up. So let me go back in here and look at charge densities. So here's the doping profile. In the semi-classical case, right? And basically there's charge piling directly up to the barrier, then nothing, and then basically a square inside the well, right? And in a quantum mechanical sense, it is not piling up hard against the barrier, but it's penetrating a little bit in the barrier and it's decaying, so it's smooth, and it is smooth on the inside, okay? So now you can also look at the yes?
If you have a charge localized in a quantum dot and you want to find out what kind of field you would apply to the quantum dot containing the charge to another quantum dot.
Yeah. Well, you actually get that out here. We'll look at that. Okay. So, so here's now charge like this. It's smooth, right? And we built in this GUI that here, this orange here is sort of what we would consider in the well. And what we have in the emitter is sort of in the light blue, right? And we can integrate over that region, and you can actually see that charge is piling up in the well, and then it's emptying out. Okay? So you have, as you ramp up the voltage, current starts to flow, right? And we talk about how electrons are rattling around in the resonant tunneling diode, right? That means they're present, right? So there's charge in there, right? And that charge actually wants to get repulsed electrostatically, right? Because it's more charge than belongs, because the doping is down here, but here's the charge, right? So it likes to reject that charge out. What happens? This resonance here is moving not perfectly linearly, but it's a little bit pushed up, okay? And then eventually the well empties out and the resonance falls down, okay? You can make this in a harder sense. You can make the structure a little bit asymmetric, where you would say charge, you make it harder for the electrons to get out on the collector side, right? So they can come in easier. Let me make it not, make it the same width, same width, but I want to change the height, because then all the plots will nicely overlap still. So I'm going to make the barrier taller, okay? I'm going to do the same thing. It's going to run for a minute or two. So what do you think would happen? What happens if you make one of the barriers taller? Come on, it's not like you're in video recorded or something. Nobody can hear your voice. Yes, but maybe not, because we're applying a voltage, right? So that's exactly right. There's an accumulation of charge, because the electrons can come in from the emitter easily, and they can't get out to the collector as easily, right? So basically the quantum well is very well connected to the emitter, not so to the collector, so charge will accumulate in the device. So what would that do? A what? Exactly right. So that means, so the potential is raised. What does that mean? Yes, fine. What does that mean? Sorry? Speak up, I couldn't hear you. Yeah, it's like a capacitive charging, good. What does that mean? No, current will be there. But think about it this way, right? You're pulling on the collector side, right? You're wanting to apply a voltage, right? And you want to pull this down. And the charge is piling up, right? It starts to float up. That means to get the peak current, I have to pull much harder down, right? So I have to apply a higher voltage to get the same peak current. So the whole curve will shift to higher voltages. What effectively happens, your whole IV curve leans over a little bit. It'll lean over and get linearized. Okay? So see this IV here? All right, it's much more linear. If you want to compare that to the just the original plot here, right? Here's the original. And here this guy leans over, gets linearized, and it goes to higher voltages. Right? So why is that? So now you go back into this plot here. So here is this asymmetric structure, transmission coefficient. And here, look at this trace of the resonances now. All right, so I'm plowing through, and this resonance starts to hit the Fermi sea, okay, the blue line right here. Right? It's almost like a bobber on water, right? If it goes down, it'll accumulate more charge, and the potential will push it up, right? So it's sort of resisting being pulled down. So here you should see, well, you see it here in this plot, how charge is accumulating inside the well, more and more, right? Until the electrostatic potential that is applied is strong enough to pull that full bucket that is trying to float up, or the charge bucket, or the bobber, until that force is strong enough to pull it all the way down. Okay? And when you pull it all the way down, it empties out. Okay? Alright? So then you see that in the trace of these eigenenergies, right? It's like the energy, the resonance starts to bob up on the Fermi sea, right? and it resists being pulled down, and then eventually you pull it down. Okay? Does that make sense? All right. So, what would happen if you flip the barriers? What does that mean? What? That's right. Does anybody object to that? Everybody's clear? Then we don't do that exercise. What happens if you take this structure and ramp the voltage the other way? What happens? Any wagers? I'm gonna start the simulation and then we'll see what you guys think. Any wagers?
The current is larger. The current will be larger because as long as you pass through the first barrier, the barrier on the second one is the resistance will be lower.
Yeah, all I'm doing is though starting from high voltage and going backward. I didn't flip the barrier. All I'm doing is, so here's how I would suggest to think about it. So here's this Fermi sea, okay? And you have now a resonance that roughly goes down linearly until it sort of hits the Fermi sea, right? And then normally you would have thought it goes like this, right? Sort of linearly, ballpark, right? So now this resonance hits the sea of electrons, and here's this other window that you need to be aware of. Here, this is roughly EF, and this is roughly EC, right? That's sort of the window in which you have a lot of electrons, right? So basically here, it means there's no supply function, right? So the electrons are empty, right? So eventually, this guy might bob up here for a while and eventually pop down, right? Like that. So what happens so this is when you come this way, right? So what happens when you march this, the other way? So what if you come in from here? This is what should happen, right? Because down here, there's no supply. There shouldn't be electrons in there, right? So you build in a hysteresis. And it's an interplay between, is this window big enough and is the charge potential float up strong enough to create it? Okay? So I'm not sure on this default geometry if that's what happens. We'll see in a second. I don't think it happened. Yeah, I did a little bit. No? So here are the last two. See, it's a little bit different, but the voltage spacing is not enough to resolve it. But you can play with that and actually build in a hysteresis like that. Okay, and that's the argument. Does everybody understand the argument, or is that not clear? Sure. All right. So we have identified that you have to have a window over which you can transmit charge, right, or let charge into the system, right? So here's my bandpass filter. I pull this filter down in voltage, right? In an ideal sense, it would run linearly, right? Forget details. And as it starts to hit the Fermi sea, this bucket of charge or this bobber gets filled up with charge and it gets repelled out, right? So it'll start floating on top of the Fermi sea until the potential that is actually yanking on it is strong enough to pull it all the way down. Okay? And then it'll follow basically this linear law because there's nothing that pushes it up, right? Now if you come from the other way, you can follow this linear path, and unless there's a process that fills an electron, or fills the state up here, and there's no supply function, that state is empty. Okay? So it'll follow this linear path until the supply function lets it have a content. And in that case, then it'll as soon as it gets a little bit of charge, it's like the bobber again. It pops up. Right? And therefore you have built-in a hysteresis. Okay? Does that make sense now? Yeah.
This is due to the charge in the channel has to go back to the source.
No, it's just purely the charge accumulation in the well. The charge accumulation in the well basically would like it to pop out this, push the charge up, because it doesn't belong, because there's no doping. Okay? Okay, so the well, the notch here has little to do with it. Okay? Yeah?
This light green curve that we are always talking about, and cumulative current then.
Yes.
Should we not follow the deep green? I mean, like at the beginning, why it's a state function?
Repeat, I'm sorry, I can't hear you.
The light green curve that you are saying.
This one here, somewhere like this? This guy? Yeah.
So it's kind of a state function, right?
Yes.
So resonance is somewhat, but
Yes.
why not at the beginning when there is a current flowing, where the transmission coefficient is not zero? It should have a value there too.
I'm confused. So at 0 voltage, you mean?
No, when you are increasing the voltage.
So I'm increasing the voltage now, right? So I'm basically getting a step function at exactly the resonance energy, right? It's 0 here.
So shouldn't be the sum of the deep green current that is there? It's not summing up that current?
Yeah, that's what it does as a function of energy, right? So it takes the light green curve is the integral of the dark green run from minus infinity up to here, up to here, up to here, up to here, and it plots it up to a certain level. I call it the running integral, right? Meaning, if you only integrate it up to this energy, in this case, you would have been just fine. Meaning, there's nothing much in the current density that's up here. Okay? But up this point here, say what I have now, 2.16 EV, that is the running integral up to this point right here over this dark green. Okay? I just stop the integral and then I keep going with it. You still seem puzzled. It's like this. Where is it? So I total is the integral from minus infinity to basically plus infinity over dE of J of E. Okay? That's I total. Right? That's the total current. But I can also define a J twiddle of E. Right? And I define that as 1 over I total times the integral from minus infinity to E dE of J of E. Call that E prime. Okay? So I'm just integrating partially up. Right? And whenever there's a strong contributions, I will see a step. And whenever I don't add much, there's no addition, and it just is a flat curve. Okay? Does that make sense? I mean, that then allows me to really identify really easily where's current flowing, right? So you can see right here's a strong difference between peak, there's a lot of charge flowing through this ground state resonance. And if I am in the valley, the resonance has basically emptied out, and most of 50-50 is running through the upper state now. Okay? Does that make sense? All right. Any questions on this RTD tool? Everything is clear as mud? Okay. Should we try to do this PCPBT tool to answer your question real quick? I'm not I hope it'll answer it, but I'm perfectly willing to go out on a limb. All right, so I think, if I understand you right, I want to do, I need a couple more barriers. Oh, maybe not. All right, so now you're asking, if I make this negative, would it matter? Like this, right? And then set these guys, well, then I don't have that, need to have that many, I'll make it easy. So like a 2 barrier like this, or even easier, a 1 barrier like this, and set this to 0.2, and set this to 0, and this to 0.2. Sort of like that. Okay. I'm not sure what happens. I hope the boundary conditions are set up properly. This looks bad if it's integrating to 12,000 nodes, 24,000 nodes. That's not encouraging. There's probably an issue in there of setting the edges to something non-zero. So let me try this. Nothing wrong with going on slippery ice and trying something. All right, so let's try this again. We'll do it this time like this. 0. What? 0. Then 0.1. Let's see what this does. Yeah, all right. So there's a quasi-bound state that sits above. Okay? Just because you modulated the potential. Does that sort of answer your question, sort of, or not?
Define it like this and the previous one didn't match?
What do you mean? Yeah. 2 barrier structure. Oh. Why would it? I'm confused. So if you do a 2 barrier structure of what now? 0.1 height. And okay, like that. Let's see. I don't see why that should be the same. That's a very different structure. Right here, the resonance is confined, roughly sitting at, oh, here it is, 32 millielectron volt. The previous one, I mean, here it's a confined state that sits inside the barriers, right? Here, it's not even computing the confined state. It's a quasi-bound state that sits above. One could argue maybe there should be a state in here. And this tool will not resolve that because it, I don't think this tool will resolve it even in the tight binding. method, because I don't think it has resonance finding in it. Oh, I have to reconfigure. Yeah, this tool does not evaluate the true eigenstates of the system. It just looks for the transmission function and tries to find the maximum. So if you have something where there's actually no transmission, but there might be a confined state, it will not find it. Versus NEMO, the code, the RTD negative code, will actually compute the complex eigenstates of the system, even if they're not coupled to the leads. Well, it'll find them. Okay, those are two different things. Okay? All right, any more questions? Oh, there's one more cool tool I'd like to show you. Yeah?
So can you create a small gap between contact and the sort of first barrier? A very small gap, like on the order of 3 nanometers.
On what tool? Is PCP RTD negative or what?
Resonance and diode. RTD.
Okay, hold on. Hold on. First of all, we're going to kill this guy before we run out of resources. So now you're asking something about the RTD. What would you like to try? This is not the RTD, right? Oh, it is, yeah. So what would you like to try?
On the left side of region 1 is the contact, right?
Here, yeah. Well, yeah. Yeah, we treat all of this as a contact.
Can you create a small air gap between...
Air gap?
Yeah, air gap, like on the order of 2 nanometers. Just a gap so that contact doesn't really touch region 2.
Air gap?
I mean, does it physically touch the region 2?
Well, this is a heavily doped semiconductor, right? Back here, you might have another metal contact to it.
So where is the metal contact? Is it on the left side of region 1?
Yeah, it's basically way, maybe even further on the left side of region 1. But the point is, this is a heavily doped semiconductor over here. So it acts like a semi-metal. Right? We had, oh, now it's running something, sorry. Oh, here we go. Oh, this is PC. No, this is RTD negative. I'm sorry. So, if you look at the charge, I'm sorry. This is not RTD negative, right? This is the PCPBT. So in a minute, it'll have it back. I take that, earlier I had a comment that PCPBT doesn't have resonance finding in it. I think it now does. I think we upgraded it to have resonance finding. Yeah, it has it now. So you can do this. So you can, to make my point here, you have if you consider this a central well, and you wanted to make this point 2, and this point 3, point 3, right? So you can have a sort of a staggered quantum well, right? So you have a truly strongly bound state in the middle. If you do this in tight binding, resonance on, this should find a very sharp resonance that will have almost no transmission to it. See this even on a log scale, this is just minuscule. It is extremely narrow. So the resonance finder actually doesn't aim for just finding the one here in the transmission coefficient. It actually computes the complex eigenvalue of the structure. And with that eigenvalue calculation, it gets the position of the resonance and it gets the width of the resonance. Okay? It's not just a hunt and peck. It actually does an eigenvalue calculation now. All right. Going back to this one question here. So you would like to, so look at this here is a heavily doped semiconductor. It's degenerately doped. The Fermi level is at 41 millectron volt above the conduction band. This is like a quasi-metal, right? There's tons and tons of states, and they're all occupied with electrons, right? So that's what we call it contact. But further out on the left, there will be still the metal contact. Okay? So we don't need, I'm not quite sure what you mean by air. I mean, if you think STM tip coming down, or?
I think I just misunderstood the dot.
Okay, this is like a layered device, sandwich.
Okay, so you have this contact metal touching the heavily doped semiconductor, right?
Yeah. Well, it's like a stack. Think of it as a epitaxy stack. So you have, say, gallium arsenide, and then you dope it heavily, gallium arsenide, and then here's your barrier, aluminum arsenide, gallium arsenide, aluminum arsenide, gallium arsenide, gallium arsenide, metal. Okay? And then you might have another metal gate here, metal. So you have a metal contact to extremely heavy doping. Here's your central device, and here's your heavy doping. Okay?
Can you, so if you have something like this, let's say this is one, quantum dot, and in contact with this is a heavily doped semiconductor here.
Mm-hmm.
And here you, instead of having contact metal right, in physical contact with this, you have a small gap here.
Mm-hmm.
It's like, if it's right on the surface, then when you can...
but this is already a three-dimensional object, right? Here's a quantum dot.
Yeah.
Well, there's no three dimension, there's just one dimension here. This thing is infinite, right? I draw it as a column, but you have to think of it from a numerical point of view. It's infinite in the plane, coming out of the plane and in here.
Yeah, so all these are stacked one on top of the other, right?
That's right, but they're infinite in the lateral size. In order to make this a quantum dot, you would have to etch it and actually give it some size.
Yeah.
We don't do that right now in this tool.
Okay.
Okay? All right?